Hello and welcome to Nexus Medical Media. In this video, we're going to talk about glycogen metabolism. We're going to talk about the general characteristics of glycogen, the synthesis of glycogen called glycogenesis, and the utilization of glycogen or breakdown, that's the reversal of glycogenesis called glycogenolysis. In a separate video, we are going to talk about gluconeogenesis. That will be a separate video, right? But this video will conclude by talking about just regulation of glycogen metabolism, right? So let's start with the basics. What do you need to know about glycogen, right? So glycogen is the most important carbohydrate storage medium in the body and is found in the cytosol, right? Cytosolic granules, right? So you need to remember that, living things, upon taking up food, you don't have to utilize all of it. You think about tomorrow, you store it somewhere. So plants store glucose or these carbohydrates in form of, and animals store these carbohydrates in form of glycogen, right? So the total glycogen storage in humans is usually 400 to 450 grams, and this will provide glucose for 12 to 48 hours. Let's say you did not eat for 12 to 48 hours. This glycogen will help keep you alive, right? So in the liver, it's about 150 grams, right? So stabilization of glucose when needed is the primary function of this glycogen in the liver. Next is the muscle. Muscle stores about 250 grams, and this one is energy storage for muscle, right? And then in the extracellular matrix, that's 15 grams, 0.1% of the extracellular matrix. You also need to remember that red blood cells or erythrocytes do not store glycogen. Okay, so on this diagram, you can see it's highlighted here. How do you stain for glycogen histology? It's called periodic acid shift staining, right? So it's histochemical technique used to visualize polysaccharides such as glycogen, right? So you just need to remember this method of staining, periodic acid shift. Right, so the basic structure of glycogen, right? So this is a branched polymer consisting of multiple linked glucose chains, right? It has branches and linkages, right? So in branches, you need to remember these bonds: 1,6 glycosidic bond and these 1,4 glycosidic bonds is in the linkages, right? So in a straight chain like this, let's just look at this glucose molecule, right? So it is a carbon 1, 2, 3, 4, 5, 6, right? On 6, that's where you have OH, right? So here you have again 1, 2, 3, 4, 5, right? So this one is 6. So for this chain, this linkage to exist in this way, you have this bond called a 1,4 glycosidic bond. But if you want to make branches are formed between 1,6 glycosidic bond, right? So number 1 will be this one, and number 6 in this case you can see is this one, right? So 1,4 and 1,6 glycosidic bond. Right, so the first thing, glycogen synthesis. How does this happen? This is a 4-step process. Step number 1 is the synthesis of UDP glucose. Right, so what is UDP glucose? This is an activated form of glucose and is the building block for glycogen synthesis and glycogenolysis. Right, so you have to remember your enzymes, basically glucokinase. So you have this glucose, it enters the liver via GLUT2, right? Upon entering the liver, let's say the hepatocyte to be more specific, it enters the hepatocyte via GLUT2, and upon entering, it's converted to glucose 6-phosphate plus ADP, and this happens in presence of this ATP, and the enzyme is glucokinase. In the muscles is hexokinase, but you need to remember the glucokinase in the liver. All right, so now you have your glucose 6 phosphate. This is what you need. So this one will be changed to glucose 1 phosphate. It's just removing the phosphate from carbon 6 to carbon 1. The enzyme responsible for this is called phosphoglucomutase, or just an isomerase, because the glucose 6 phosphate and glucose 1 phosphate is just an isomer, just changing the position of the phosphate. Now you have this glucose 1 phosphate. There is an enzyme called the UDP glucose phosphorylase. It converts glucose 1 phosphate to UDP glucose and pyrophosphate. Right, so you have to you are mixing this glucose 1 phosphate and UTP, uridine triphosphate, to make UDP glucose. Right, so is shown by here. You can, as you can see, this is your glucose 6 phosphate. You can see the phosphate on carbon number 6 via this isomerase enzyme, that's phosphoglucomutase. You are changing the position from carbon 6 to carbon 1, that's glucose 1 phosphate, and then you take UTP. This is UTP, right? So if you put it here, it becomes UDP glucose and pyrophosphate. Pyrophosphate is a very important source of energy, right? So if you break this pyrophosphate, you have energy that you need for these reactions to continue, right? So and now your end product that you have here is UDP glucose. Let's put it somewhere and talk about glycogenin, right? So glycogenin is an enzyme of a homodimer protein that is at the core of each glycogen unit and is the starting point for glycogen synthesis. Remember, your UDP glucose is in the pocket. Okay, right. So glycogenin catalyzes the formation of short glycogen chains by polymerizing a few UDP glucose molecules, right? So glycogen synthesis can only add glucose molecules to a chain that is at least 3 glucose molecules. So this is just the basic structure of glycogenin, this homodimer, right? Okay. Now let's talk about the chain elongation, glycogen synthesis, right? So this is a key regulatory enzyme that binds UDP glucose molecules to the growing glycogen chain, and it catalyzes the formation of 1,4-glycosidic bonds between the UDP glucose and the hydroxyl group of the carbon 4, right, is C4 at the free end of the glycogen chain, right? So as shown here, let's say you have your glycogen is being formed here, right? And this is your UDP glucose. Using glycogen synthesis, you have this glycogen, so you have added this new, and at the end you have your UDP. You are throwing it away and take another UDP glucose, putting it here, leaving glucose and throwing away the UDP, right? So it will be recirculated and used again to make UDP glucose. But here our aim is for elongation of this chain. So the bonds, 1,4-glycosidic bonds, are being formed here, right? And the enzyme glycogen synthase. Right, so this enzyme is actually a rate limiting or rate determining enzyme in glycogenesis. Right, so we made a long chain of glycogen. It's just a long one string with the 1,4-glycosidic bond, but you know, for stabilization it needs like branches, right? So the branching enzyme is an enzyme with a glucosyl transferase activity that introduces branches of glycogen chain to allow for further chain elongation at multiple sites within the glycogen complex, right? So it catalyzes the formation of 1,6 glycosidic bonds, and this happens by hydrolyzing a chain of 6 glucose units of the original chain. I will just show you using a picture, and then attachment of molecules to carbon number 6 of another glucose unit within the original chain. And these branches are introduced at least 4 glucose units apart from one another. Right? Let's say this is your glycogen chain with 1,4 glycosidic bonds, right? So it's this one, right? On glycogen synthesis, you have added this, but now you want to make branches, right? So you branches, you'll be cutting this and you'll be putting it here, right? So this is happening. We have removed this part, and we joined it here. So it's branching enzyme, and in this case this one is forming 1,6 glycosidic bonds. The 1,4 have been formed by glycogen synthesis, and the 1,6 debranching enzyme. Right. So we have made this polymer, the storage unit. It's very stable. It has which bonds? 1,4 and 1,6 glycosidic bonds. Now, how do we utilize the glucose? Let's say this is starvation. It's not fed state, it's starvation. You don't have glucose. You have hypoglycemia. So how do you get back the glucose, right? So the first step is cleavage of 1,4 glycosidic bonds, right? So, and this one is done by glycogen phosphorylase, right? So a cofactor of this glycogen phosphorylase is called vitamin B6 or pyridoxine. It cleaves off the glucose 1-phosphate through a phosphoric reaction until 4 terminal glucose residues remain on a branch, and this is referred to as limit dextrin, right? So these are the glucose 1-phosphate. So you'll be releasing these one by one, 1, 2, 3, 4, 5. At the end, you just have glucose 1-phosphate, right? Just put it on the side. Then the second one is to remove like these branches, cleavage of our alpha 1,6 glycosidic bond. This is done by debranching enzyme because they have been formed by a branching enzyme. So it's just a reverse. Debranching enzyme is an enzyme that has a glucosyltransferase as well as glucosidase activity. All right, so just one more time, I just want to remind you that we have synthesized 1,4 glycosidic bonds using glycogen synthase, and we have reversed or we have cleaved this bond using glycogen phosphorylase. Alpha 1,6 glycosidic bond is formed by the branching enzyme and is cleaved by debranching enzyme. It's that simple, right? So the first step is glucosyltransferase, right, or 4-alpha D glucotransferase, right? So this will transfer 3 out of 4 remaining glucose residues of the branch to a nearby, right? So basically, you remember when I was saying that if you look here, we will be removing these glucose 1-phosphates until we have 4 at the end. So what happens to the remaining 4 here? That's where these 3 will be transferred. So the remaining 3 will put it on the long chain. Let's say we are cleaving this, right, and then we take these 4 and we put them here on the long chain, so that the glycogen phosphorylase will be cleaving that long chain, right? So we will be remained with what? With only 1, right? So this will be a glucosidase activity, right? So this clips off the remaining glucose unit, that's alpha 1,6 glycosidic linkage, from the branch through hydrolytic reaction, and will release non-phosphorylated free glucose molecule and a linear chain of glycogen, right? So we've removed the three. Yeah, we have removed the three here, and we put them here, and then we have one using this glucosidase activity. This one is actually glucose. Remember, what we are releasing here is glucose 1-phosphate, but here we have glucose, but it's little. It doesn't help us much, because we need more glucose, because remember, we are starving, or we are in a hypoglycemic state. So what do we do? Now you have to convert glucose 1-phosphate to glucose 6-phosphate, right? So in the muscle, there is instant metabolization of glucose 6-phosphate during exercise. That's glycolysis. Right? So if you remember the process of glycolysis, the first step is to convert glucose into glucose 6-phosphate. Right? But now we already have it. We just converted glucose 1-phosphate that we took using glycogen phosphorylase from the glycogen in the muscles. We just have to run down this glucose 6-phosphate into glycolysis. The enzyme hexokinase will convert free glucose to glucose 6-phosphate, because remember I said the last glucose was released as glucose is only one. You convert it to glucose 6-phosphate and then run it down glycolysis, right? But in the liver, glucose 6-phosphate is the enzyme that you use to make free glucose, right? You just have to remove this phosphate on carbon number 6, and then you have free glucose. This is actually faster than running down through glycolysis, right? So this free glucose will be released into free circulation, and it will increase the serum glucose, right? So let's say you have your glycogen here, right? Using glycogen phosphorylase, you have glucose 1-phosphate, and using the mutase, you have glucose 6 you have using the mutase, you have glucose 6-phosphate, and then that glucose 6-phosphate, you using glucose 6-phosphatase, you have free phosphate plus glucose, and then glucose will be available in the serum, and then reversing the hypoglycemia, right? So a part of glycogen is not degraded by glycogen phosphorylase and debranching enzymes, but in lysosomes by lysosomal alpha glucosidase. And deficiency of this enzyme will result in Pombe's disease. That's glycogen storage number 2, right? So remember, I didn't mention one thing on this glucose 6-phosphatase. Some people do not have this, and they have a condition known as von Gicke, right? So we'll talk about it in glycogen storage diseases, right? So, but I remember when I was talking about right now I was talking about these lysosomal enzymes, right? So if you don't have this alpha glucosidase, you have Pombe's disease. Then Cori disease is a type of glycogen storage disease, type 3, that is caused by deficiency in the glycogen debranching enzyme. So if you don't have this debranching enzyme, you have Cori's disease. Then McArdle's disease is a glycogen storage disease characterized by deficiency in glycogen phosphorylase in skeletal muscles, right? So if you don't have this phosphorylase, the most common sign is hypoglycemia. Here in debranching enzyme, again, is hypoglycemia, right? But we'll talk about this later in glycogen storage diseases. Now let's talk about the regulation of glycogen metabolism. Please guys, if you've been continuously sticking onto your screen and watching me trying to explain this concept, thank you very much, right? Thank you. And please make sure you give it a thumbs up. Just that will give me the energy to continue making these videos, right? So on regulation, glycogen metabolism is primarily regulated by hormones. Which hormones? Insulin, glucagon, epinephrine, right? So in skeletal muscles, glycogen metabolism is also regulated allosterically by ATP, AMP, calcium. And regulation is based on phosphorylation and dephosphorylation of the key enzymes. Let's say you have the glycogen synthase. This glycogen synthase is responsible for glycogenesis, right? So it's active when dephosphorylated, right? So if you phosphorylate it, you inactivate it. Then glycogen phosphorylase is used for glycogenolysis, and this one is active when phosphorylated. If you dephosphorylate glycogen phosphorylase, you have deactivated it. Guys, this is okay. This is something else, right? So on glycogen phosphorylase, this glycogen phosphorylase is actually regulated by another enzyme called glycogen phosphorylase kinase. Right, so this will help in the conversion of inactive glycogen phosphorylase to active glycogen phosphorylase. So let's just talk about these hormones. What do they do? Let's say you have high serum glucose. You have high serum glucose. You need to store it. You need to convert it to glycogen, right? So insulin will help as an uptake of glucose from the blood to the cells, and then from there you make you activate glycogen synthase and synthesize glycogen. But let's say you have hypoglycemia, you have low serum glucose. You need to reverse the process. You need the glycogenolysis, right? So what do you produce? You produce a stress hormones like epinephrine and glucagon. You can remember it this way. Glucagon is produced when glucose is gone, and this is actually responsible for glycogenolysis, and the enzyme that will be activated there is glycogen phosphorylase, right? So it will be phosphorylated there. Okay, so just to conclude this video, I just want to highlight the next video that we're going to make is about glycogen storage diseases.